Welcome to Math 104, Chapter 5.1, where we finally talk about exponential functions. Now, exponential functions have outputs that are multiplied by a fixed number for each unit increased by the input. Now, this has the formula you're seeing down below, where b is a positive real number. So b, for example, is any number. So b is a number, and x is the exponent, the variable. So for example, perhaps something like 4 to the x, or 2.3 to the x, or 1/2 to the x, or sorry, 1/3 to the x, all would be an example of an exponential function. Now, before we move on, we do have a few different variations of this equation that you might be seeing in the future. Now, this is the most basic one, but we can tack on a few things such as something called a multiplier, where this a is just your constant or your coefficient of b. So that would be your coefficient of b. You can also have something being added over here to the other side. So we have a constant. Of course, up here we can have many more things. X can have your coefficient, could be added or subtracted to another value. Let's say d, a can be negative, you name it. But this has just like the most basic form of your formula that you'll be seeing in the future. So that being said, can you circle the functions that are considered an exponential function? So the ones that are exponential, we said, have a number in the bottom in your variable in the exponent. So something like 3 to the x, or negative 2x to the fifth, or even 1/2 3x minus 4 in that exponent. Now this one would be considered linear right here, and the other one would be considered cubic. The remaining are going to be considered exponential functions. Now, graphs of exponential functions, because we have not seen an exponent in the your variable in the exponent before, they're going to have a different looking graph than what we have seen so far. And I'm sure you guys have heard, like, it's rising exponentially, right? It is going so quickly, it's rising so quickly, or it's falling so quickly, it's decaying so quickly. So your graphs are going to look like either of these two variations. Now, the difference between it is that on your left here, we have a growth function. So if we have f of x is equal to b to the x, this is when b is greater than 1. So we are working with positive big numbers, not big numbers, but numbers that are greater than 1. So numbers that are greater than 1. Whereas this one is considered a decay. This occurs when your function, when b is between 0 and 1. So what are some values between 0 and 1? Well, values between 0 and 1 are any sort of decimals or fractions. So b is a fraction between 0 and 1, or a decimal. Now notice both here that we are greater than 1 or less than 1, but we are not equal to 1. This is because if we are equal to 1 to the x, if we do 1 to the 2, that's still 1 to the 3, that's still 1 to the 4, that's still 1. So what we're doing is actually we're going to be creating a solid line, and it's horizontal. So that's why we can't be at b is equal to 1 at any point in time. So that being said, can you find the following? An x-intercept, a y-intercept, domain, range, and something called a horizontal asymptote, if you know what that is. So your x-intercept, actually we'll skip x-intercept for a moment. Let's do y-intercept because you can clearly see your y-intercept on both graphs as being 0, 1. So that one is pretty easy to get. Now, let's take a look at your x-intercept. Now, we haven't seen this type before where we're crossing through. Normally, we cross through an x-axis in order to get an x-intercept. And we have seen it before where we might not have an x-intercept, but this one is actually very unique. Notice that it's trying to stretch itself out to try and touch the x-axis here in both cases. Now, what they're not seeing is that we're not actually touching. We're trying to get as close to your x-axis as possible. So as you continue your values in on either side of the infinity. Do you know what that is called? Well, that is called a horizontal asymptote. A horizontal asymptote is a line that you cannot cross. So y is equal to 0 in this case. Why it's y equals because horizontal lines are all y equals. So horizontal asymptotes are usually represented with a dotted line. We'll actually thicken that line up just a little bit. It just means we cannot touch, we cannot cross this line. Which means, are we ever going to have an x-intercept? If we know x-intercepts are where x is a number and y is 0, well, if we cannot touch when y is equal to 0, we're not going to have an x-intercept. It is not possible for this graph to touch this line, which means your domain and range will do some interesting things when we go to put it into interval form. Well, with your domain, we always read from left to right. So left, right, your x value is trying to get as small as possible, trying to reach out for this line. So we're starting all the way out at negative infinity. And then as we continue to the right, we're skyrocketing, but still going up and out. And that would be on both graphs. Again, this one is going up, but we're going up and out for your x values. Whereas this one, we are just trying to continue on to getting to your y is equal to 0, while your x values are continuing to grow. Now your range, right? Your range, we said y cannot be equal to 0. It's that invisible barrier. So we're going to start your values at 0, but notice that we're not going to include them. We're going to get as close to possible at this line, and then we're going to skyrocket up to infinity. Now an asymptote we had just talked about is when a line continuously approaches a given curve but does not meet it at any finite distance. It just means that we cannot touch your asymptotes, which is why we have no x-intercept, which is why your range, we can kind of quote unquote start at 0, but we're not really achieving at 0, just like we can't achieve infinity. So now let's try it out with some algebraic and graphic forms to find some of these values. So if we know that f of x is equal to 2 to the x, and we want to find f of 6, so algebraically, we know that x is equal to 6. So instead of having 2 to the x, we can actually take away that x and raise it to the 6. Now, what does this actually mean, right? 2 to the 6th really means we're multiplying 2 6 different times. 1, 2, 3, 4, 5, 6. 2 is being multiplied 6 by itself 6 different times. So what is 2 times 2? Oops. 2 times 2 times 2 times 2 times 2 times 2. That should be 64. We can also punch that into your calculator. Uh, let's just do this one. Actually, let's do your TI-84. So you have 2 raised to the 6th power is 64. And we'll do it graphically here in a moment as well. And let's try it again here. So pause the video, see what you come up with. Instead of 2 to the x, we have 2 to the 4th, which is equal to 2 times 2 times 2 times 2. So 2 times 2 is 4, 2 times 2 is 4, 4 times 4 is 16. Now let's try these graphically. We'll do this one in your TI-84. So if we were doing it graphically, we have y equals 2 to the x. And we are just going to go on a very standard viewing window, and there you have your value. And if we're trying to do 2 to the 6, notice that 6 is over here to the right. So let's go ahead and expand a little bit upwards for your y max. Now we already know your answer, but let's try and go to 50, see how that looks. We are getting higher. We are noticing that that blue line is going to intersect that 6 down below in your x value. So let's get a little higher. Let's try 80. Okay, so much better. Now you can evaluate if you'd like, or you can hit second trace value. And this is when x is equal to 6. And there you have y is equal to 64. Now, if we were to do it in your Desmos graphing calculator for the next one, actually, let me go back before I do that. We could also hit second table and then scroll down until you see where x is equal to 6. You notice that x is equal to, when x is 4, we have 16, x is 3, we have 8, and that's just by hitting second table. Now, if we did the same for your Desmos, we have y equals 2 to the 4th. And notice that it actually already spits out y is equal to 16. We could also go ahead and change that to an x, and we can drag your finger along to see until we get to the 4. We would need to change your output a little bit. Or we can also hit that little settings button and then down to the table. And we just need a few more x values, and then you'll see the 16 there. Now, what are exponential functions used for in the real world? So see if you can come up with some ideas on what exponentials are really useful for. Well, we can use them for stocks, investments, spreading of disease, carbon life, carbon dating, / half-life, and the list could go on. But these are some really good ones to get us started, and we'll be seeing a few of these different types of ideas here. So speaking of some investments, one that we're going to encounter is called compound annual interest. This is only one of many equations that we have as far as investments go. Now, to detail out a few things, you can change this S to an F if you would like. Your textbook just uses an S. Sometimes it uses an A, but let's define a few things. P or PV stands for your present value. This also just stands for your initial, your principal, something that you have right here and right now. Which means if that P stands for present, F stands for future. Some future value, something that it'll grow to, amount to, anything that says you're going to be having this in the distance. Rate is R, and T is time. Notice that you have the exponent variable. So then let's suppose that inflation is predicted to average 4% per year for each year from 2012 to 2025. Write a function that gives the cost of a $10,000 item T years after 2012. Now, this sentence is going to help us for the remainder of the problem, but for right now, when we're trying to create this equation, let's just use it as T for now. So pause the video, see if you can take this equation and the parameters given to put those ideas together. Well, they are telling us that your present value is equal to $10,000. We know your rate to be 4%. Now, if it's been a minute since you have done a percent to a decimal, you're going to take your decimal that's located on the right of the 4 and move it over 2. Now, when you move it over, you're just going to fill in the remaining spot with a 0. So we have 0.04 is now your rate. So now we're going to say your future value is equal to your $10,000, 1 plus your rate, 0.04, raised to, right now, we're just going to use it to the T. Now let's clean that up a little bit and say we have 10,000 times 1.04 to the T. And no, you cannot multiply this 10,000 to this value because 1.04 has your variable in it. So based on that variable, it will change the amount that comes out. So now let's graph the growth model for time 0 to 13 and find an appropriate window. Now it does tell us that T is the years after 2012, which we recall that for the year 2012, what does your T value stand for? Well, T is 0 for 2012, which means if T is 1, we have the year 2013. So keep that in mind. We just haven't seen that one in a little bit. However, it does come back to us a lot. So let's plug this into your calculator and find a good window. They also tell us your window here for time. So this is your X value window. And we can find a much better window. So let's use, let's do this one. Oops. So we have 10,000, 1.04 raised to, raised to the X. In your window, we said we're going to be going from 0 to 13. And there isn't much difference between 0 to 13, so your scale can remain at 1. Now let's, before we, I'm just going to actually reset this to just 10. Now notice we can't see much of anything of your graph. We do have the appropriate X values, but it's your Y values that's the issue. Now, the reason it's not coming up is because what is your initial investment? Well, your initial investment is what you started with in the bank account. So if that is $10,000, right? Our Y values are only at -10 and 10. So we need to get above and below this value. So if we want to see clearly this starting value, right? Pick a number that's generously above 10,000 and below 10,000. Now, below 10,000, depending on what your graph looks like, it could be at 0, it could be at 5,000, right? So that's kind of up for debate, but just make sure we're able to see your graph. So if we were to change your Y max, let's see, instead of, if we did $10,000, right? You still can't see it because it's right at the tippity top. We are just missing it by a small margin. We also want to perhaps change your X scale because from -10 to 10,000 is huge. So probably 500 or maybe 1,000 would be a good idea. Oops, we can keep that for now. Now let's get above, let's say 25,000. Oops. Okay, now we can actually get a good sense of your graph. This is an R8 graph, an R8 uh, window. As much as I would love to see a curve, they kind of limit us because we're only going from 0 to 13 here. So this would be an R8 starting window. A previous section had us go from 5,000 to 15,000. So this can be up for debate. So now it says, predict and interpret the cost of an item in 2020. So in 2020, above 10,000, Y max, Y min, below. Okay. So we said 2020 is your year. But we converted all of your t's to have a specific value. So what is the value for 2020 for t? Well, the difference between 2012 and 2020 is 8. So t is equal to 8. So we can either look at the table, so second table, and look for where t is 8, where you see it here. And we can actually click on it and it'll give you the decimal form as well. Or you can go ahead and hit second, trace, and value, and then plug in an 8. And it'll again give that same value. Okay, number E. So E is actually a number, very much like pi, right? Where it just continues without bound. It should be 3 dots that suggest it keeps going. Now, therefore, E is an irrational number. So the graph f of x is equal to 2 to the x, or sorry, it says graph f of x is equal to 2 to the x, f of x is equal to e to the x, and f of x is equal to 3 to the x on the same coordinate. So we're going to get rid of these. 2 to the x, oops. Nope. Y equals, let's do 3 to the x, and the last one, y equals, and your e, I believe, is okay to use the one here. Yeah, there you go. Back to, there you go. Okay, so we have purple as 2, black as 3, and red as E. So what do you notice about your graphs? Well, we should notice that all of your y-intercepts are passing through the point. That's great. We all have um, the same domain and range, and better yet, we have the same um, horizontal asymptote, and you can just see it here. We're trying to get as close to that 0 as possible. Now, it is showing that y is 0, but that is misleading. If we really zoom in, it's trying to get as close as possible. Now, what do you notice about your black and purple and red lines? Black, purple, and red. Well, it looks like the black and the red are kind of together, and that purple one is not so much. That continues as we continue to go up. Your purple is just way out there, and the other two are really, really close. Any reason for that? Keep in mind your colors. Black is 3 and red is E. We said E is just about 2.7 or so, and we have 3 here, right? So notice that these two values are kind of close to one another. So E is very similar to a 3 to the x graph. That's all that we're pretty curious about, because E is a number just like pi. Now, because E is a number, we can actually use it to represent a compounding continuous equation. So like last time, you can change S to F if you like, F being your future value, P being your present value, or your principal. E is just E is your number, R is your rate, and T is your time. So if we were to try this next example, we have $10,000 is invested for 15 years at 10% compounded continuously. What is the future value of an investment? So as long as they say compounded continuously, we are able to use your equation over here. Now, your equation does have a small nickname. It is called PERT, because if you put these all together, they look like the word PERT. Keep in mind, though, R and T are raised to the E. So they have told us we have a $10,000 investment. Your T is 15 years. Your rate is equal to 10%. Moving that over to decimal places, we get 0.1. We are compounded continuously. So that being said, we have F is equal to $10,000 e to the 0.1 times 15. That'll get us to some value. Let's try that out. Now, I haven't done decimals in a minute, so we'll do this one here. So we have $10,000 times E. Let's see, going to your ABCs, we have E over here raised to the 0.1 times 15. And there you have it. We have 44,816 and 89 cents. Now I'm going to also do that on your graphing calculator as well. So E on decimals, you're just going to use the ABC button on here. There are 2 locations for your E. One is right above the division sign to the right, and the other one is right above the ln sign, or right below the log on your left-hand side, which is kind of over by 7 and 4. So when we go to type in your 10,000, the most common one that we're going to use is the one found to the left, and notice that it's in blue, so we're going to hit second ln, and then we can go ahead and hit the remaining of your question. And there you have your graph. Now I'll show you if you did not use the right hand or the left hand one, and instead you use the right hand one. Notice that the difference is the first one already put it to a power. This one did not, so then you have to raise it to the power. Just a very slight difference. It comes out with the same answer. Now let's try it again. Now pause the video and see if you can do this one solo. It says if $10,000 is invested for T years at 9% interest, compounded continuously, so we can use the above equation, the future value is given by, and it gives you your equation. Graph the function for 0 is less than or equal to t, which is less than or equal to 15. And again, where your s is 0 to $50,000. So let's graph that one in Desmos. So we have 0 and 15, 0 and 5. Okay. So we said we are going from 0 to 15. We are then going from 0 to 50,000. And I just want to double check that. Okay, so your graph should look something like this. Same thing in your other calculator. Now they did not tell us the scale, but keep in mind your scale on Desmos is just your step. Your step for 0 to 15 can just be 1 if you want to put it on there. The other one from 0 to 0 to $50,000, you can be a little bit more generous. So perhaps $100, $200. Okay, so we've graphed it. That looks great. It says use the graph to estimate when the future value will be $18,000. Round to 2 decimal places as needed. So we can have, if this is a y amount, because keep in mind x is equal to time in years. So sorry, it's no longer x for us. It's right now it's t. And s is equal to a dollar amount. So if they give us a dollar amount, they are really giving us a y equals amount. So if we come up here and we go to y equals $18,000, what should we be looking for? Well, we can see a clear intersection, which is the most important feature on our graph. So we can go ahead and click that, and you'll notice that it's going to take 6.5 years in order to get to $18,000. Or sorry, that's your T, your X, whatever. So if we were to put this in a sentence, we can say it will take 6.53 years to reach, or for our investment, to reach $18,000. Now, if you are doing it in your TI-84, you're going to do the exact same thing. You're going to put this value into Y2, and just make sure that when you graph it, you can see a clear intersection, and then you can go ahead and hit second trace. Now, notice that right here, the decimal place is very specific. So at times your chart may not work. So now it says what year will give the future value of 24,596 and 03 cents. Okay, so one more time. Oh, because did they tell us we changed our years? Now they don't give us any sort of context to the year, but like as to if we had to change it. So let's try it one more time. We said 24,596. 24,596 and 3 cents. Okay, so one more time, we're interested in that intersection. It'll take us 10 years. Now, that being a much nicer whole number, we could have done your, um, what are these called? Your tables and keep going until we get to that amount. But again, just be hesitant with that because notice that we had up here, we are looking for that $18,000 mark, and it goes from 17 160 to 18,776. So we could conclude that it's got to be somewhere within those two numbers from your previous example. Same thing over here. We can conclude it is 10 because beside the 3 is a 1, which would round it for just that variable. So 10 years. Now you will be seeing something like scientific notation on some of your calculators in the future. So scientific notation we'll just cover briefly is just a short form of your value. So if we have 1.2 e to the fourth, or you could say this is the same thing as times 10 to the fourth, this is just saying we're going to take this decimal place here and move it over 4 times. It's just a shorter version to write your number, especially if it's something like 14 decimal places over. Now the same goes for the below, except now we're working with a -4. Instead of moving your decimal to the right-hand side, this is actually an extremely small number, so we're going to be moving it to the left-hand side. And again, just filling in where you have the empty spaces, zeros. So there you'll see, again, the two numbers. So be cautious, make sure you're reading your values correctly. If you see an E or times 10, that just is in scientific notation.